And how are you guys? This is the second lab. We'll be working on motion of a falling object, a free fall, as we would say. It's the physics 2211 section M. I'm Swapnil Vittal for you guys, and this is the spring 2023 session. The flow of this presentation will be really simple. We'll be understanding the fundamental physics principle involved in this presentation. We'll also be analyzing a falling object using the app called Tracker. We'll compare then the computational model built using GlowScript with our observation from Tracker. We'll also take in account drag and terminal velocity and compare both of them. And we'll also consider a case where we throw the object downwards, thus, and the object has an initial velocity. The fundamental physics principles used are very easy. First is the Newton's second law, which is the final velocity is equal to F net upon the mass multiplied by the change in time plus the initial velocity. We also call it as final velocity is equal to acceleration multiplied by difference in time plus initial velocity. The weight force, of course, is mass times gravity, and then there's the drag force. We'll be predicting the position of the object using the formula final position is equal to V average multiplied by time plus the initial position. And the net force on the object will be the force by gravity plus the drag force. No other forces are present on the object. We have assumed that there's no wind or air. The initial velocity of the object in this case is zero in magnitude. Here's a video of the free falling object. The free fall was a bit too fast, but as you guys can see, we have drawn a graph for the change in position and the change in velocity of the object. The object in this case is a paper ball. The observations are first, the mass of the object is obviously known and constant, which is given. The observation start time is zero. The observation initial velocity with the slight error is zero. With the initial position is with a slight error zero, and the initial velocity again is zero. The time of last observation was 0.4 seconds, and the final position is as given. The computational model without drag. I had to change a little of my code and had to apply the Newton's second law and the force for position and weight force and the formula for position and weight force, which is as given. Uh, Here's a link to my GlowScript code if you want to check this out. I'll also give this in the comments. Let's compare both of these. There are a few errors in our computational model and the model that we got from Tracker. The first is the ball drifts a little along the x-axis. Also, we haven't accounted the drag force in this case. In the future, I'll account for friction and drag. Also, I would like to perform this in lab conditions as for better accuracy. The computational model with drag is as given. We'll apply the Newton's second law, the formula for position, weight force, and in this case, drag too. It's as given. I had to change my GlowScript code a little, but here it is. Let's compare both of these. The ball again drifts a little along the x-axis. In this case, there's a little video distortion as the object is in 3D, obviously, but we record the video in 2D. There's also a perspective distortion, and I would like to perform this again in lab conditions where the object would be more of a point object than a paper ball. What does it mean? The terminal velocity, the model with drag predicts the terminal velocity, which in this case will be when the force from gravity is equal to the force by drag, and the net force hence becomes zero, and the velocity becomes constant. What if the object is thrown? I made a tracker model for this again. And first of all, there will be an increased drag force to determine if the object starts from rest and the object has an initial velocity of 2 meter per second in the y direction. The terminal velocity though remains the same in both the cases. Thank you so much for listening so patiently to my slides, and I'll see you guys in the next lab. Hope you like this. Thank you so much. Bye.